I'm going to talk a little bit about matrices today to kind of help you with some of the cross product stuff. First part is a 2 by 2 matrix. If you're going to evaluate the determinant of a 2 by 2, it's basically the difference of the products of each of the entries. So if you look at this 2 by 2 up here, we're going to say A times D minus C times B. If we apply that down here to these 2 by 2 matrices, I'll do at least one of these. The determinant of this 2 by 2 would be 1 times 7 minus 5 times negative 4, or 7 plus 20, which is obviously 27. Same thing over here, this next one, we can say 3 times negative 2 minus negative 1 times 4, or negative 6 minus negative 4. Negative 6 plus 4 would be negative 2. And lastly, 7 times 3 minus negative 2 times 10. This is 21 minus negative 20, or really 41. So that's how we evaluate the determinant of a 2 by 2 matrix. For a 3 by 3, it's a little bit more complicated. First thing we'll talk about is minors. For minors, we're actually going to cross out the row and column. So if we're going to figure out the minor for this first term right here, in row 1, column 1, we're going to cross out row and column, and you can see what is left in this matrix is right here. And that is what we evaluate the determinant of. So the minor of row 1, column 1 would be simply the determinant of those 4 values, just like we did above. If we were going to go on to the minor of entry 1, 2, meaning row 1, column 2, again, we cross out row and column, and you can see what is left in the matrix, and that is what we are going to evaluate the determinant of. If we do row and column for entry 1, 3, meaning row 1, column 3, again, what is left are these values right here, and that's what goes in the determinant. So if we were going to look at this matrix down here, we wanted to evaluate the minor for row 1, column 3. I'm going to cross out row and column. And again, that's row 1, column 3. What is left would be negative 1, 2, 5, 7. And we're going to evaluate the determinant. That's negative 1 times 7 minus 5 times 2. Or negative 7 minus 10, which is negative 17. Let's do another one. We'll say row 3, column 2. I'm going to cross out row and column. Here's row 3, column 2. Okay, so what's left in that matrix would be 1, 3, negative 1, 4. And we could evaluate the determinant of that, which would be 1 times 4 minus 3 times negative 1. Or 4 plus 3 would be 7. All right, so let's talk about cofactors briefly. So the cofactor is simply negative 1 to some power times the minor. And again, the minor is what we just did right here. It's just the 2 by 2 determinant. So if I wanted to evaluate the cofactor of row 1, column 1, and we can use matrix B up here. And we'll see if we can evaluate. We'll do this one over here. Cofactor 1, 3. So if I was going to evaluate that, that would be negative 1, and A and B are 1 plus 3 respectively. And then we already evaluated the minor 1, 3 up here. Minor 1, 3, we got a value of negative 17. So I'm going to say this is negative 1 to the 4th times negative 17. Negative 1 to the 4th is obviously 1. So this is simply negative 17. So again, when you're doing these, just recognize that you're just simply multiplying it by 1 or negative 1. If I was going to do this first one, 1, 1, I would have negative 1 to the 1 plus 1 power times the minor for 1, 1. This would be negative 1 to the second times the minor for 1, 1, which gives me 1 times the minor for 1, 1. In this one, 1, 2, you can probably see the pattern here. Negative 1 to the 1 plus 2 times the minor for 1, 2. That's going to wind up being negative 1 to the third. And that's going to be negative 1 times the minor for 1, 2. So the pattern here, looking at a 3 by 3 matrix right here in the middle, it's going to go positive, negative, positive, meaning this is negative 1 to the second, this is negative 1 to the third, and negative 1 to the fourth. Negative 1 squared is positive, negative 1 cubed is negative, negative 1 to the fourth is positive. And you can see this is kind of the pattern for all of your cofactors. So we're simply going to take the minor and multiply it by the right sign. So let's talk about how to evaluate the determinant of a 3 by 3 matrix. So to do the determinant of a 3 by 3 matrix, we'll just use the front or the first row as an example here. We're going to simply add up all the cofactors of any row. So going across, again, here's my minor. If you look at the values here in our 2 by 2 determinant, we're simply going to multiply that value, A11, or the entry in row 1, column 1, times the determinant of that 2 by 2. And then we're going to do the next one. If we cross out row and column, again, you can see what's left right here. We've entered our entries in the 2 by 2 matrix that we'll evaluate the determinant of. And then for the third one, cross out row and column, you can see right here, that's going to match up with our entries here. And the one thing I do want to point out is we're multiplying each of these by the entries themselves. There is one little nuance here, which is that negative. That is coming from our cofactor right here, that middle term being negative. So let's see if we can do a quick example of something like this. We're going to evaluate the determinant of the following matrix, and we're just going straight across the top row. And you can see if we cross out row and column, this is where we're getting our 2 by 2 matrix right there. If I did row and column for the second entry, you can see that's where this 2 by 2 matrix is coming from, and the third one follows that same pattern. And again, that negative value in front, it's not a negative 2 right here, but we're adding that negative sign because of the pattern of the cofactors. So you can evaluate this, and I'll show that briefly. This is what it winds up looking like, and again, we're just evaluating the determinant of each of those 2 by 2 matrices, and you wind up getting 0. Now, this is the exact same value you would get had you used a different row. Now, remember when we talk about the cofactors here, the second row has a different pattern. It goes negative, positive, negative. So if I had used the second row here, I just want to show you what that would have looked like. So we're using this entry right here. The first entry would be 4. And we know we have to add that negative in. And if I cross out row and column here, I get 2, 3, 8, 9. Second entry, we know it's going to be positive. I'm going to cross out row and column. So I'm going to say plus 5 times the determinant of 1, 3, 7, 9. And then if I did the third entry in that second row, cross out row and column, you can see it is 6. I'm going to add the negative sign because they alternate. And I get 1, 2, 7, 8. This would actually give you the exact same value if you evaluated this. You're going to wind up getting 0 for the determinant of the matrix. I could do the same thing in the third row if I wanted to as well. And let me show you briefly what that would have looked like. We'd have 7 with the determinant of that matrix, minus 8 times the determinant of 1, 3, 4, 6, and plus 9 times the determinant 1, 2, 4, 5. Again, all three of these are going to be the same exact thing. It does not matter which one. You don't have to do all three. Just pick one that works easily. And again, if you look at this, this is positive, negative, positive. That's coming from this third row right there. Okay. So let's talk about how to find the cross product of two vectors. So let's just make up two vectors. I'll say vector A in ijk form would be I plus 2j minus 3k. In vector B, we'll say minus j plus k. If I'm going to calculate A cross B, I'm simply going to put these into a 3x3 matrix, and we'll find the determinant of it. My first row is just going to be ijk. Second row is going to be the entries in A, meaning 1, 2, negative 3. And the entries in B are going to make up my third row, 1, negative 1, 1. And if I want to evaluate the determinant of this matrix, I'm going to use the top row, I times the determinant of 2, negative 3, negative 1, 1, minus, remember that the cofactor has a negative sign in that middle term, negative j times the determinant of, again, crossing out row and column, 1, negative 3, 1, 1, and plus j times the determinant, plus k times the determinant of 1, 2, 1, negative 1. And let's evaluate these determinants. This looks like I times 2 minus 3 minus j times 1 minus negative 3 plus k times negative 1 minus 2. So this looks like negative I minus 4j and minus 3k. That is the cross product of these two vectors. Last thing I just want to mention to you, there is a formula for the angle between two vectors. It looks like this. If you have two vectors, we'll call it u and v. The angle between them is given by this formula here, where the cosine of the angle between them is u dot v. This is a dot product over the product of the two magnitudes. Again, this is the notation for the magnitude. But if you think about what this means, if cosine theta equals 0, theta would be equal to the inverse cosine of 0, or 90 degrees, or pi over 2. So if this value is 0, that means that these two vectors are 90 degrees apart. We call those perpendicular, or in the case of vectors in 3D, we call that orthogonal. So that's this word right here. It basically means perpendicular in 3D space. So for this value to be 0 up top here, all that has to be 0 is the dot product. So what you want to recognize is anytime the dot product is 0 between two vectors, they are perpendicular or orthogonal to each other. So you'll see that on edgenuity. If you take the dot product of any two vectors and you get 0, that means they are orthogonal or perpendicular. That's the quickest way to test for that.